Even though we use the idea of multi-threading all the time in our daily lives, the idea of hardware multi-threading typically is pretty confusing to students. So let's work on that here. So in this example, we are going to use a fictitious processor that can run one instruction per clock. Notice that there's one fetch and decode unit, there's one yellow execution unit, but has support for 2 hardware threads. So it's going to interleave these threads because notice it can only do one instruction at a time. So each clock it's going to have to pick which thread it wants to run an instruction from. So let's chart it out here. So what I'm showing is time is going along the horizontal axis. You see time and clocks. And what I'm illustrating is when each thread is being chosen by the processor to run its instructions. So let's imagine we're running a program that has this pattern of instructions where a thread performs 3 arithmetic instructions like adds and multiplies, followed by a load that takes 12 cycles. So it'll look a little bit like this. So thread 0 is on the processor. Let's say the processor runs 3 instructions from thread 0. And then comes that memory load. And so thread 0, we can't run any more instructions for thread 0 for the next 12 cycles. Now after those 12 cycles, the data comes back from memory. We can run the next 3 instructions. And so on, and so on, and so on, if your program sort of in a for loop or something like that had this pattern of 3 math ops followed by a load with a stall of 12 cycles, and so on, and so on. Now the important question to ask here is, what is the utilization of our processor when it's just running one thread? And you can read it right off the diagram. It's the fraction of time where the diagram is colored blue. And if you kind of look at every repeating segment, which is 15 total cycles, 3 maths plus 12 latency, only 3 of those 15 cycles are actually doing useful mathematical work, doing operations. So 3/15 or 1/5, 20% of the time, this processor is stalled. Now comes the idea of hardware multi-threading. Now remember, this processor was able to support 2 hardware threads. So when thread 0 is going to stall, the processor can switch right over and choose to run instructions from thread 1. So notice now that in the thread 1 row, I'm showing that when thread 0 stops running instructions, when the end of the first blue bar hits, the processor just switches over and starts running the 3 instructions that it can run from thread 1. And this process also just repeats. So now let's think about it. If I look at every 15 cycles segment again, well, I'm doing useful work, or in other words, the blue bar is covering a column for 6 out of those 15 cycles. So I've increased my utilization by 2x. I'm now running at 40% utilization. And if I continue to add threads covering more and more of the stall time, when I get up to 5 threads, if you look carefully, when thread 0's data has come back and thread 0 is ready to run again, we have filled all of that time by running the other 4 threads. Now you might think, well, more threads must be better, but that's not actually the case because we're already running at 100% utilization. We can't run instructions any faster than we are now. So if we added more threads to the processor, here I have 8 threads on my processor, I'm still running at 100%. So I'm not going any faster, I'm just interleaving more stuff. And actually, if you take a look, the difference between the 8-thread version and if I take a step back to the 4-thread version, notice that thread 0, since it has to share the processor with more of the other threads, actually takes longer to complete its work because it only gets 1/8 of the processor. So notice how the blue segments are spaced out here. And notice that the blue segments are even more spaced out when I'm working with 8 threads. More threads can also cause problems like all of these threads might be contending for caches, and maybe they actually will require more memory accesses or more bandwidth if more of these threads are running concurrently. Okay, so now I'm not going to change the processor, but I am going to change the program now. So it's still a 2-threaded processor with memory latency of 12 cycles. But now I'm going to change the program so that it does 6 arithmetic instructions before that memory load. So the schedule kind of looks like this: 6 useful instructions, 12 stall cycles, 6 useful instructions, 12 stall cycles, and so on and so on. And now out of every segment, repeating segment that's of length 18, 6 plus 12, 6 of those cycles, or 1/3 of them, are actually useful mathematical work. So we're running at 33% efficiency with 1 thread compared to what we had before, which was 20%. And so now with this new program, which has more math for every memory access, we end up using the processor in full using only 3 threads. So app programs that have a higher ratio of arithmetic instructions to memory accesses can actually get by with fewer threads to reach high utilization. Okay, so let's summarize. A processor with multiple hardware threads has the ability to avoid stalls by performing instructions from other threads when one thread must wait. This is a really simple idea. Basically, it amounts down to, if you can't make progress on one thing, go do something else. Also keep in mind that multi-threading does not reduce the latency of memory access. In all of my examples, latency remained 12 cycles out to memory, regardless of how many threads I had, or regardless of what program I was running. Multi-threading only hides the effects of latency, the potential stalls, by doing something else when the processor would otherwise be waiting around. Point 2. A multi-threaded processor hides memory latency by doing work from other threads. That means that you need fewer threads to hide that latency if you can run a lot of instructions in those threads. So the more arithmetic or math operations there are per unit memory access, the fewer threads you need to push to high utilization. So as a programmer, you want to try and push your ratio as high as you can go. All right, hopefully that helps.